Doing good. Today's topic is the topic of conceptual discussion on refractive index and the concept of refraction. See, many students have some insight into refraction because this is taught in junior classes also. But when you reach class 12th and you do the topic of geometrical optics, one of the physical observation is the refraction, which is a bending of light. So what I'm going to do now is I'm going to show you some bullet points and the key points you must understand about refractive index, especially in class 12th now, and how it correlates with the whole process and the way we approach it. Now you may have a picture that refraction, so the topic is refraction, and definitely it is as perceived by a lot of people. This is popularly the bending of light. Okay, so this is definitely bending of light. That's a layman's way of looking at it, but a lot happens inside this bending, which should be clear in your mind. So if you have refractive index is another thing we will discuss. Okay, so we will talk about refraction, we will talk about refractive index. Okay, refractive index. Okay, let's talk about it. Now if you have a medium, which is medium number 2, and this is your medium number 1. Now generally, when you see the refractive index mentioned somewhere, refractive index of water is 4/3, the glass is 1.5. Those are absolute refractive indexes. Okay, well, let's talk about bending first. We will talk about refractive index later. So if you have a light which is coming in from object of which is less dense, so refractive index is also called as optical density. Okay, there's another word for refractive index called as optical density. And optical density has more to do with speed of light. So what we're saying is, in medium 1, the speed of light is high. So we will say this medium is a high speed medium. Okay, this is a high speed medium, and the speed of light is higher here. So the speed of light, the speed of light is being referred to. Speed of light. Okay, so let's say this medium is vacuum. Okay, so we can easily write that the speed of light here is 3 into 10 raised to power 8 meter per second. So this is our speed of light in vacuum. It's a high speed medium. Okay, now it is entering a medium which is a low speed medium. Okay, so this is your low speed medium. When we say it's a low speed medium, the optical density is more. So when I use the word optical density, I will concentrate on speed. Okay, so speed is lower, and maybe this is all water, and so when the light enters at a very high speed and enters into a zone of low speed, this is what happens. If you draw a normal here, which is this, if you draw this normal, and all the angles are measured by normal, so the light bends towards the normal. Okay, so the light bending, so this ray of light is your refracted ray, and this ray of light is the incident ray. Okay. So the whole focus of this diagram is to tell you that you're moving from high speed to low speed. Okay. And the word I'm using, the terminology being used is optical density. So you study refraction from two different perspectives. One perspective is the perspective of high speed and low speed. This is one. Okay, and you can see when you move from high speed to low speed, you move towards the normal. So in a reverse situation, which is if you reverse these trays, if you move from low speed medium to high speed medium, you will bend away from the normal. So this is one way of looking at it. All right. So the speed changes because of change in optical density. This high to low speed happens because of change in optical density of the medium. Now let's talk about the more popular way of looking at refraction, which is straight away bending. So you have a interface between the two surfaces. You have a medium 2 and you have medium 1. Okay, and the light comes in, as in geometrical optics, it comes in like this, and there is a normal. If medium 1 has less refractive index as compared to medium 2, then this is called as less dense and this is more dense. The light bends towards the normal, right? So this is your normal, okay, and this is your refracted ray. This is refracted ray, and this is your incident ray. So this is your incident ray. Okay. Now, if you see the phenomena is same, the bending has taken place. The bending has taken place. This actually is more about speed of light. Okay. This emphasizes on speed of light. But the popular way of looking at this, which is the refractive index, does not focus on speed of light. It doesn't get into that level of detail. And this popular method, which is your conventional refractive index, has a focus qualitatively. What it does is it expresses this, that the refractive index of the material, is 2. For example, the medium 2 with respect to 1 is given by sine I upon sine R. So that's your popular Snell's law, and this is your angle of incidence and this is your angle of refraction. Okay, so incident, refraction, the way you express this bending mathematically here is using refractive index is equal to sine I by sine R, and this particular one, it's a refractive index of 2 because the refracted ray is, so if the refracted ray is inside this, you write the subscript down, and the incident ray medium, which is the medium upwards, is this one. So you will see the two perspectives. One perspective is the refractive index is sine I by sine R, and this is your typical Snell's law. Very, very important for your examination. Okay, so this is your Snell's law. And now let's come back. So this part I think is pretty clear and a lot of people understand it. Let's however look into the optical density. One way of expressing the optical properties of when the bending takes place, the speed changes, and let's express that speed in certain format. Now if you have to write optical density, which is nothing but refractive index, what you do is, instead of expressing this as some kind of the So what you do is, instead of writing sine I by sine r, what you do is you express this as, you know, speed of light in that medium. Okay, so let me write this as the speed of light upon in medium 1 divided by speed of light in medium 2. Okay, so I'll just bifurcate so that it's easy for you, and I will just draw a line here also so that you know this is the boundary for your, you know. So what you studied here was optical density. What you studied here was the concept of refractive index, and what you're studying now is optical density, which is nothing but refractive index, but the expression has become the speed of light, you know, in the medium 1 divided by speed of light in medium 2. So here the assumption is, you know, the light is coming from 1 to 2. Light is coming from 1 to 2. This is your incident ray and this is your refracted ray, which is something like that. Okay, and the speed of light in optically dense less mediums, air and vacuum are optically less dense. The speed of light is higher, and therefore I use the word high speed medium. So high speed medium corresponds to low density, and low speed of light refers to high optical density. Okay, so for example, if the refractive index of 2 with respect to 1 is 4 by 3, and you know the speed of light in the medium 1 is given to be, for example, it's vacuum we took, is 3 into 10 raised to power 8, and we want to find the speed of light in the medium 2, we will write this as V2 is equal to 9 into 10 raised to power 8 divided by 4. Okay, this is the way you're going to write this. Meter per second, obviously. Okay, this is meter per second. So if you see this whole thing, so you can get numericals where the focus is optical density and the speed of light is the focus, and then there are numericals where the emphasis is on how much bending has taken place, vis-a-vis this situation where how much speed loss or speed gain has happened in the light. Let me give you another dimension to this. If you have light coming in from an optically less dense medium to an optically more dense medium, something happens to light. So if you were to, you know, express light in the form of some kind of wavelength, you know, and I will just draw 1 lambda, 2 lambda, and 3 lambda, and 4 lambda, and 5 lambda, and 6 lambda, and 7 lambda. And you notice the wavelength of the light here is lambda here, you know, maybe it's a monochromatic source of light. What you will find is when it enters the other medium and it is bending, the wavelength in an optically dense medium, you know, goes down. So this is your lambda dash, which is a wavelength in lambda 2. So if you're entering an optically dense medium, the wavelength will go down. And another way of writing the speed of light, you know, can be, if you write the speed of light as, let me just write it for you, as mu 2,1 is equal to lambda into c divided by lambda in the medium number 2, this is medium number 1, into c, right? Sorry, frequency. So write this as frequency, because you know the speed of light can be written as frequency, you know, gets cancelled. Okay, I've used speed is equal to lambda into f here. Okay, so this is your lambda and that's your frequency. The frequency does not change. So if you move from one medium to another medium, the frequency does not change. What changes is the wavelength. Okay, so what changes is the wavelength. This aspect should also be clear. So when you're doing numericals on optical density. Not only you have to focus on the speed of the light, but sometimes the questions can be pertaining to the wavelength. It should be clear in your mind that the frequency of light does not change with the medium. Only the wavelength undergoes a change. I hope this two perspectives, the optical density, which is more to do with high speed and low speed as it relates to optical density, and the refractive index, which is more to do with bending of the light, and dwells more on Snell's law, to calculate the angle of refraction and angle of incidence, given that the medium changes. It's clear in your mind. I conduct live classes for JEE and NEET examination. If you're a parent watching this or a student watching this who's very keen to build career and is ready to put in labor, I teach physics as a very conceptual oriented physics, and if you are ready to put in hard work with me, then I can assure you of success, tremendous success in JEE mains and NEET examinations. I have tremendous knowledge of mathematics also, and I've taught maths for many years. So I'm a good combination of maths and physics, and can make you an expert in solving and cracking numericals for entrance examination. I have a YouTube channel which is having 1,500 YouTube videos. Please watch them. You will get a lot of conceptual clarity. A lot of numericals are solved from very famous books in that YouTube channel. Join my live classes. You would love them and be successful. Thank you very much for your time today. Good luck.